Thanks very much for that, Quinn. Appreciate it. Just checking standard, that's coming through
Yes.
with the slide now. Fantastic. Thank you. Well, look, thanks, Quinn, for the opportunity, and then to Seagray, NGN Australia, for the opportunity to present. I was having a bit of a chat with Kunj in the lead up while we were sort of sitting in the waiting room for this meeting, and I want to flag, so the goal or my aim for the presentation today is to talk you through NEM connections. I think this event was advertised as NEM connections in general. The ad on there is that I'm going to try and focus more so on generator connections, because I think that's quite a relevant and also interesting area of connections with the energy transition well underway. What I will say is that in general, working through processes like NEM connections can be challenging, and in trying to prepare this presentation, I was looking at how I can make this as engaging as possible. I'll apologise if I didn't quite do that because it can be a bit dry, but hopefully, if nothing else, it's informative, and we'll leave a bit of time at the end, hopefully for some sort of robust discussions, whether that's via Q&A or by people being able to come off a microphone. So very, very quick intro from myself. I currently work as the Principal Engineer of Connections Assessment at Energy Queensland. Energy Queensland is the electricity distribution utility that services the state of Queensland via their two DNO organisations, which are Ergon Energy Network and Energex. I've spent about 10 years working across the electricity industry, mostly in Australia, but a little bit of time in the UK and USA working for distribution utilities over there, and have spent time across this generator and general connections area for the last 5 or so years in different capacities. Prior to that, did a bit of work in innovation, technology deployment, and general asset management. I did, before I jump into the presentation, want to give a shameless plug to Seagray, the NGN, and particularly the Seagray Australia NGN for the opportunities that provides. So I am in the maybe unfortunate position of being around long enough to have been a part of the starting committee, so the inaugural Seagray Australia NGN co-chair when it was kicked off back in 2011. I've now aged out of the NGN and I'm no longer eligible to be a member as of this year. So that's a shame, and maybe I hung on too long there. But what I did want to say and what I did want to plug is the opportunities that the NGN brings over the last more than 10 years, really. It's presented a lot of different opportunities, both to do networking, technical presentations, technical visits, and just general industry learning, both in Australia and when I've travelled abroad. There's been so many good opportunities. So I would say as an organisation, Seagray is very good for power industry. It's, I would say, one of the leading organisations focused in the power industry, and the NGN as a part of that gives some fantastic opportunities to network with other early career engineers and to further your own career. So can't encourage you enough to get involved in the committee, and keep an eye out for those opportunities. With that shameless plug over, before we start, I did start this presentation, I want to acknowledge that as an engineer, I think it's vital to know your limits and limitations. And from my perspective, I've got some clear biases and blind spots. So just covered my career in the industry that has been heavily focused in the distribution business, heavily focused in Australia, and particularly heavily focused in Queensland. So I have a very network-oriented view of connections, and that sort of experience has spanned about the last 10 years in total. As a result of that, I've got some blind spots. So I'm about to walk you through a very complex process, which has many perspectives and many opinions associated. From my side, I'm definitely representing the perspective of a sort of someone working in the distribution industry, but there are many others, so developers, consultants, transmission utilities, AEMO, OEMs, all of those different parties play different roles and very important roles in the connections process. And if you talk to different people from those different areas, they may give you different perspectives. The other one is my involvement. So particularly in my role, I'm more focused in the assessment stage of connections, which is what I'll do a bit of a deep dive into through the presentation. I'm not considering, and I'll try and sort of flag it and not, give it some recognition of the substantial effort that goes into early stage concept, scoping, financing, detailed design, construction, operation. They are obviously huge undertakings, but this presentation is going to be focused more on the AEMO connections process. Obviously, without all of this, none of that happens. And the last bit is there's obviously a lot of history. As an electricity industry, we haven't just started doing major generator connections in the last 10 years. It's grown and developed, I would say, a lot in my time being involved in this space. As I say, I think it's important to flag those different perspectives and opinions because I unfortunately can't fairly represent all of them. And so with that in mind, I wanted to throw a disclaimer in that the stuff we're about to talk about now is effectively my own opinion. It's not that of Seagrays. It's not that of the organisation that I work for or anyone else we're discussing. With those formalities out of the way, as I said, the goal of today, and this is a very, very average anecdote, but is hopefully to take the connections of process from, knowing where you start, knowing where you want to end, and maybe having a loose idea of the process to get there, to hopefully, within this metaphor, peeling back some of that shroud. So I don't think I'll get to the point where I have everyone fully understanding, because it is, as I said, it's a changing area. It's an area where I even continue to grow after being in this space for quite a number of years. But hopefully at the end of this, you get a bit of a better picture for what it takes through the formal connection process. And then therefore how, how you might be able to play a role, or what the different opportunities and challenges and areas that we could do things differently are around that. There's a very quick overview. So I'm going to cover three main areas, I should say. With I'm particularly keen to have some open discussion and a slight preference, Quinge, for some off-mic discussion if we can. I don't know whether that's possible with the meeting set up, because I think that's super valuable. What I will do is start with an overview of the connections process. I'll then do a deep dive on some of the specific stages. So again, more aligned with the work that I do, and trying to explain that in a bit more detail. And I'll finish up with some of the opportunities for early career engineers. So jumping straight into it, again, I'll acknowledge that a lot of what I'm presenting, there is good information online. At the end of this slide pack, and I'll try and pull it up at the end for a few seconds so it's included in the recording, there is a lot of really good resources across different areas, but AEMO in particular, as you would expect, have a lot of good resources. And what I'm presenting is borrowing heavily from their connection process overview. With that, I'll jump into the start of the connection process. So effectively any connection, and this is not just generators, but any connection that would be looking to connect to a network will go through a pre-feasibility stage. And when we say pre-feasibility, that's really with the developers looking at what they're looking to do, scoping that, understanding what size they're looking to operate to, understanding what technologies. So if you're talking about generators, solar batteries, wind farms, gas generation, all those different things, and weighing up either based on their business strategy or based on the area that they operate in, what they're looking to achieve. So where they're looking to connect, what size, and what their ask is, and coming up with some high level finances around that. So we think this is going to cost this much. As I said, this is one of those areas that there's a significant investment in this stage just to get from an idea through to, okay, let's explore this in more detail. And what you'll see on each of these as I flick through, try to give an indication of timeframes and costs. Take them with a bit of a grain of salt because they can vary. From there, this is really the first formal stage beyond often working within the organisation. So then you move into an inquiry, and this will often be one of the first major engagements with potentially AEMO, but definitely the network service provider, and it's what you call a preliminary inquiry. So under the NER, network service providers are legally required to have this service and to offer this service. it's essentially a free service, which is that a proponent can come in and put in a preliminary inquiry, and the NSP then sort of furnishes that connection applicant with information about our network. So that can be, these are our networks in this area. These are the capacity that we have available. Here's some assets that may be at risk of exceedance. Here's some other operational risks. Again, this is often very high level. It's not sort of detailed engineering assessments, but it's a first pass, back of the envelope style of this is what you're asking for. This is your proposed location, sizing and arrangement. This is what we think we can do off the back of that. And what you'll see at the end of that is the formal response is called a preliminary response to inquiry. And that usually takes a few weeks up to a month. There's actually legal timeframes that you are required to respond within unless otherwise negotiated. That gets the proponent, so the person looking to connect the generator, to a point where they've maybe got some idea of what they're looking at. There's maybe a connection option with some high-level scope, but it's, again, all very much back of the envelope. They'll then decide from there to say, well, look, that seems reasonable. We want to go to a detailed response to inquiry. And now this is moving into effectively a paid service. And this is where I would say the real engineering, but the real analysis is probably more the right word, comes into play. And so with this, again, the proponent will say, well, that connection, please, can we go to the next stage? Here's some more information about our, what generation mix we're looking at, size of systems. Can you please proceed with a detailed assessment of that connection option and come up with a scope and estimate? So a lot of that's around steady state modeling. I won't jump into that too much now because that's one of the deep dive areas for later. But effectively, this is really where we're starting to get in and actually assess that connection, understand the impacts. And usually, again, scale of cost-wise, you're looking sort of around, between high tens of thousands of dollars often to maybe $100,000. So it's a significant investment for someone that's effectively still a speculative development. And out of that, they would get a sort of confirmation of, yes, this is doable. We've sort of confirmed from our side that the impacts of this connection are manageable, or actually, no, we need to do augmentations to support that, and we'll come up with a proposed works to connect. So effectively a scope and estimate that says to deliver this connection, we need to build X new feeder or augment transformers, or actually it's all manageable within existing network capacity. We just build the dedicated assets to go from where the power lines are at the moment to your service point. Often, I guess the reality with this process is often can go through a number of cycles, and maybe, as the proponents refining their offering, as they're understanding the costs, that might get revised. So all through there, what you could be looking at is sort of 6 months to a year. And again, that's sort of probably heavily discounting this pre-feasibility stage, which could be sort of any length of time for an organisation to come up with their sort of rough plan and financials. Once you progress through that detailed inquiry stage, now you're getting to the really serious end of things. So if the proponent goes through all of those stages, says, okay, we're settled on an option that we think is reasonable, we've seen that scope and that costing, I shouldn't say high level costing, but that costing, we think that's reasonable, or we're happy to proceed with that. Then they'll go into a pre-application stage. And by application, this is effectively now they're saying we want to move ahead with this connection. And so at this point, your sort of scale of costs escalate probably by a factor of 10, really, because you're starting to look at the customer will come. So this is now where it's starting to get very generator specific. All of that stuff previously is often, common for loads and generators, but for pre-application with generators, they'll come with a proposed, what you'd call a performance standard, including some modelling to demonstrate how they would perform. So with generators, it's extremely important within the NEM to ensure that generators connecting are able to meet a sort of standard performance capability and behave in a certain way, particularly during things like contingencies or voltage disturbances or frequency disturbances. So the application pack would be the customer coming and saying, look, here's what we what we've got. Here's how we think that's going to operate. Here's what we'd propose to you to make that work. And so, as I said, this is a document. These are models. These are often technical assessments to say, we can manage reactive power flows and voltage and our impact or our contribution to network voltage performance. Particularly for inverters, harmonic emissions are a big thing because they're switching plant. So understanding that, yes, we can meet our harmonic emission requirements. Yes, when we energize our big connection, often fairly big connections, that's not going to negatively impact the network at that instant. And again, we'll get into this in a little bit more detail later. And the last bit of that's having some preliminary designs and secondary systems information, so protection. And if you may have heard that there are sort of references to R submissions, so R0, R1, R2. That effectively, that milestone or that stage is called an R0 submission. So it's your first formal submission with all of the information about your generator. Within that stage, this now moves to the NSP. The NSP receives that application. They say, okay, we understand what generator performance standard you've suggested. We agree with that, or actually we need to work on some bits. And again, I'll talk about this a little bit more later, but there's within the NER, there's sort of 3 defined levels of meeting standards. They are automatic access standards. So effectively you meet the sort of, not quite, but gold standard. You meet at the automatic pass level and you've demonstrated that you can do that. There's then a negotiated access level, which is often and usually a sort of lesser level, but you've negotiated with that NSP. And then there's the minimum access standard, which is effectively the bare minimum that would be accepted. Usually most people will try and hit the automatic access standard because that's the sort of industry agreed. If you can do this, you should be okay. But as a part of this, this is the NSP, I guess, receiving that package, running through their own due diligence. So confirming that, yes, we agree with your models and that your generator can actually do that. Potentially doing some wide area models. And then off the back of that, looking at system strength remediation. I'm going to skim through this a little bit now because I'll talk about it in more detail later. Appreciate, and if that seems very, very vague, that's because I will talk about it later and I don't want to cover it twice. That package then, as you work through that and arrive at an agreed generator performance standard and set of models, is then sort of locked in stone as what's called the R1 submission. So that's the next stage. And you may wonder, like, effectively they've given you an R0 submission. You're now saying there's a new submission. The reality is the difference between R0 and R1 can be reasonable because there's an iterative process within there of negotiation, understanding performance requirements, refining generator tuning and performance to effectively arrive at an agreed point. And so that agreed point is the R1 submission. Process-wise, again, we're sort of talking about 6 months to a year-ish before. Now, you definitely, like, this process in and of itself can be several months to a year to go through that application stage. So again, we're probably looking on the sometimes optimistic side of 1.5 to 2 years just to get us to this point. And that's not including all of the financing discussions. So obviously throughout this stage, the developer's getting more information about what this is going to cost. That may require some reruns on their original numbers. They may be starting to move through preliminary land acquisition if they didn't already have land, working through initial tenders for generator suppliers, detailed design, and maybe some preliminary construction. So again, all of this is happening up in parallel often, and it's been skimmed over very much. This bit, I guess, what I would call out here is that is considered a major milestone. So when generators get to this point, I sort of skimmed over it or didn't mention it, but that's what you'll hear referred to. Once you get to that agreed point and everyone's locked in stone, you'll hear that referred to as receiving a 534A letter. It was effectively their offer to connect and confirmation that we accept that connection as it's been agreed by both of us. The lock is because that is a major milestone within a generator connection process. And it's actually, I mean, it's a decent financial investment to get to that point. It's also worth a lot of money because the generator is then what we'd call committed. And committed just means that you've effectively got a confirmed connection. It's been agreed with AEMO and the NSP. You've now got a lock on that connection in that network, likely also that capacity in the network. So if you're a 100, 200, 300 megawatt generator in the network, you then reserve capacity to be able to export at that level. And so as you can imagine, and particularly in distribution networks, which are, often, not in the scale of hundreds of megawatts of capacity and can be congested, that capacity and having a lock on that capacity is super valuable. And what often happens is developers may then on-sell that opportunity to someone else. So investment companies looking to get into renewables, they'll effectively say, here's, a committed connection, we'll on-sell that to you to develop in full. The last couple of stages then, which again, there's a lot that happens in this stage, and I'm doing it very, very, very high level recognition. So please, again, understand that there's a lot within this, but I'm just skimming over, is you then move towards completion stage. So obviously you now need to build the generator. You've got some committed connection. You now need to build all that. And that's both on the NSP side of things. So doing whatever augmentations are required, both in primary assets, so potentially building new power lines, substations, upstream augmentations to reinforce the network. Also, one that's often overlooked is the secondary system. So again, maybe more so a distribution challenge, but a lot of these connections are in areas that weren't made to take or weren't originally built to take multi-megawatt or tens of megawatt generators. So there's often a major investment in secondary systems, namely protection. And then obviously on the generator side of things, they actually have to build the generator and, an ability to receive and reticulate electricity around their network. So again, you're talking, obviously this is where, from a primary assets perspective, the big dollars are spent. But it's worth acknowledging that often you've worked through this whole process and really only now they're sort of progressing into actual construction and having that certainty. The last bit that I'd call out is once the system's built, you'd move into commissioning. And so it's extremely standard that you'd have staged commissioning with, if you say, using the example of a 100 megawatt generator that's coming in to connect into a distribution network, you don't just say on day zero, look, 100 megawatt generator, go for it. You're commissioned. Let's see how you go. They'll work through staged hold points and they'll release that capacity in stages. And so normally it's sort of across 3 or 4 hold points. The first hold point is effectively a 0% release of capacity. And you might ask why have a 0% release of capacity, but effectively that's just energization of the plant, often taking background power quality readings and collecting a lot of information before the generator starts. Sometimes also you just want to energize the inverters or the system that you're running as a part of your own sort of preliminary testing and commissioning. From there, you'll then move through stages. And I've put in there is sort of roughly a third. Often it works on that basis, but it might be, 20%, 50%, 100%. The thing to call out is that at each one of these stages, the generator will move to operate at that stage. So they might move from 0 to 33%. They then have to provide technical reports demonstrating that their system operated as expected over that period. And in that period, while that report's being reviewed or those sort of commissioning findings are being reviewed, they are run back to the previous hold point. So again, going through these stages can take quite a while, and is, for a system or for a generator that's invested a lot of money, is definitely, something they don't want to take a long time because, they're effectively constrained to partial operation. By the time they reach full operation, they then have to close out effectively their commissioning. And the last bit, which again I'll talk about a bit later, is providing updated and benchmark models. So everything we're talking about in these early stages was all theoretical models. It continues to be a theoretical model, but the idea is that once you've commissioned, you should have run a lot of the tests that you were demonstrating in these early stages around generator performance. You then go back and benchmark that and say, well, we actually did those tests. This is how the generator performed. Did our models match that? And that is really the last stage in generator commissioning, which is what we'd call an R2 submission. That's when you've provided your final set of models, designs, technical reports, and this is how the system performed when we actually ran it. All up, and again, this is probably quite optimistic, but you're looking at, again, 3 to 4 years until you're at that point of having everything locked in stone. You're having a commission generator with no further works required. So in summary, I'd say that the process is definitely staged and complex. One of the challenges is it's only becoming more so. So as we learn more, as definitely within a distribution business, and setting, transmission, large generator connections has been a common thing for a long time. Within distribution, it's been an area of growth and learning. So as we learn more and understand more, I think there's often more requirements that come out of that and more things that we're looking to mitigate. Also with the sort of move from large centralized, often synchronous generation that you'd consider to be often very stable to smaller inverter-based generation, that presents a whole heap of challenges, which again, I'll talk a little bit more about later. I think the other big point to take away, which is hopefully clear in that, is there's a substantial investment of time and money before the connection's committed. So other than people who are sort of looking to do those early stage developments and then on-sell a connection, if you were looking at doing that to end to the day where you first start making money, that's a good number of years and a lot of money that you're front loading to get to the point where you are actually able to make money. I think on top of those challenges, changing economic and regulatory environments, and political environments even make that less certain in bankrolling those investments. The other thing that's worth considering is definitely when it comes to getting those committed connections, it's a first in best dress basis. So often you can have multiple connections competing for the same capacity, and one reaches a committed stage first, it then reserves that capacity or that connection, and so others lose out. And that probably leads to this third point here, which is historically, and I'd say it's an area we're getting better, but there's been limited coordination in investment, which can be pretty inefficient. So AEMO with their integrated system plan and renewable energy zones is trying to trigger, definitely at that transmission level, some sort of build it and they will come mentalities where we'll say, we're going to invest in transmission in this area. That will free up capacity. You should invest in, renewable generation in particular in these areas. And then the last bit is just the challenging delivery timeframe. So again, what I presented was maybe on the optimistic side. Obviously, if things go a little bit awry or are anyway challenging, those timeframes can blow out. So now I wanted to deep dive on a couple of those specific stages. And again, this is probably based off my own interest, but I think because it's one of those areas where you can tend to spend quite a bit of time. And that's in that inquiry stage, and then as the next step in the application and completion stage. And so when I said I'd spend a bit of time on the modelling and assessment side of things, inquiry stages of a lot of steady state RMS modelling. These later stages are dynamic EMT and RMS modelling. If that doesn't make a lot of sense to you at the moment, I'm going to try and explore that a little bit more and explain what we're actually doing. First, I'll focus on the steady state RMS connections and walk you through a little bit of that. But again, just to reiterate, effectively to get to this point, we've had a generator come and connect and say, I want to connect my generator here, please. And as an NSP, you've said, okay, well, in this area, we've got this network. And based on this network, we think we could connect you in this way or this way, but we're going to have to do some more assessment to understand the impact on these different assets. And that's effectively what this detailed inquiry stage, which is what I talked about before, is doing. So what we're actually doing when you peel that back is conducting, as I said, detailed analysis to understand the impact of the connection on the network. So that's looking at, and talk about it down here, but looking at things like steady state voltage impact, impact on capacity and thermal rating, rejection studies. So what happens if this generator was to trip off, and what's the impact on the surrounding network? And another big one is, fault studies. So what's the impact on protection? What's the impact on fault rating of plan? And are we now starting to exceed that because we've just embedded, or we're looking to embed a large generator in that area? A lot of that's done in packages that I think is, if you're a power engineer, you may already be familiar with, but they're what we call RMS models, so root mean squared, or phasor models. Effectively, it assumes the whole network operates at 50 hertz. And depending on how detailed you're looking at, you may just be doing a snapshot. So like a minimum load, maximum load scenario, you may be looking at doing it over different, a bunch of studies over a year to look at how that performance changes. You may be looking at imbalanced models, but usually I'd say these are often balanced three-phase load flows. So that's the sort of studies we're doing at this stage. As a part of this, we're also then setting early stage expectations back to the generator to say, well, look, based on our studies, this is what we think we're going to need from your generator to support network voltage or to mitigate your impact on network voltage. So, you need to be able to support so many VARs of reactive power flow. You'll need to, be able to withstand some of these contingency conditions. And so it forms the basis for the proposed connection arrangement. So off the back of this, hopefully you're getting an idea of all these augmentations are required. So that's your options and scope, and costing, I should say. And then giving the customer information on what they might need to be clear on with their proposed generator performance standards. The other ones that I mentioned previously, and I won't recap too much on now, but is as a part of this, the NSPs will be setting expectations around your harmonic allocation or your harmonic emission allocation. Your connection is this, your maximum impact on power quality. So things that you might hear referred to as flicker, or the sort of measurement is PST and PLT, which is sort of short-term and long-term flicker measurements. Doing preliminary system strength impact assessments, which I'll try and do a bit more credit to later, but effectively this is particularly relevant to inverter-based generation in understanding the system strength that they require to be able to run their system stably. And then, historically, that's just been something where we've been aware of that. We've tried to understand that more and more now. There's a push towards inverter-based resources to either contribute to system strength or to demonstrate that they have low reliance on system strength. Might just have a quick drink of water there. Sorry, guys. Got a frog in my throat. So what are some of the challenges that you identify at this stage? So I would say it's been a growth area, and definitely in distribution networks over the past 10 to 15 years. So just in understanding and probably accurately modeling and mitigating those impacts, or understanding what impacts need to be mitigated, has been a growth area. The network's definitely becoming more congested. So we've been just talking about a single generator. The reality within the distribution network, it's often because it's quite widespread, because it's, provides supply into often quite remote and sparse areas. You get a number of generator connection inquiries for those areas, and they become quite congested. And they're not just one big generator. It's, often several small ones ranging across a number of different sizes from, 1 or 2 or 3 megawatts right up to potentially several hundred megawatts. And obviously that incorporates all of the rooftop systems and everything below them that don't go through this process. So more and more the network is becoming congested, not just from a load perspective, but from a what you might call a minimum load or reverse power flow perspective. And the last bit that I had called out there around the challenges is often, again, within the distribution network, it just genuinely wasn't built for generators. It was built to supply load. And I know that's a cliche that gets rolled out about one-way power flows. It's not just the one-way power flows in terms of capacity and managing voltage, but it wasn't made to be safe with lots of generators in a network area. So Protection, as I said before, is often one of the biggest impacts, and bringing the protection up to standard to be able to support a generator is often super costly. And it's not something that when you think about connecting a generator, you think, I'm going to have to maybe spend millions of dollars providing communications and protection capability to be able to connect this. You think, I'm going to spend millions of dollars putting in wind farms and solar panels and transformers and power lines and all of that. What are some of the opportunities? Definitely within this front, dynamic management of capacity. It has been done historically at the transmission level and at the NEM level. So AEMO manage the market, both the financials of the market and the bidding process, but also in the dispatch of the market via their NEM dispatch engine, or it's called NEMD. And that manages not just the financial side of things, but then, okay, if there's multiple generators bidding in to operate in an area and that results in a network constraint, how do we apportion any dispatch capacity, and how do we ensure there is no thermal constraint, or we're not exceeding planned ratings? That hasn't usually happened at a distribution level. And when I say it hasn't usually happened, it hasn't been a focus because there haven't been as many generators. It's also always been a bit further down in the network than has necessarily been valuable, but that's now changing. I'll try and rock on because I do want to leave a bit of time for discussion at the end. The last bit, and this is where you can then spend quite a bit of time, is once you move past that into the connection and you're agreeing performance standards, is in dynamic EMT and RMS assessments. So dynamic by its nature just means changing over time. So it's a time-based study. EMT is electromagnetic transient studies, or some of you may be familiar with PSCAD. PSCAD isn't the only software that does EMT, but it's the main one that's used within the Australian network environment. We'll talk about that later. The other one is just doing dynamic models with RMS simulations, so 50 hertz simulations. By definition, EMT sort of models everything. Models everything. It is the closest attempt to recreate real world environments that you can get. So it's effectively sort of modeling Maxwell's equations and all that, and propagation of waves on a sort of microsecond basis. As I said before, this all starts with performance standards. I mentioned, there's different levels. Well, so there's different performance requirements, which are these bits on the right. If you ever want to have a look, check out the NER and check out Schedule 525. 525 sets out a whole heap of different technical requirements. And these are all requirements for the generators to say, right through from what monitoring and different control capability you have to have online, through to what reactive power you have to be capable of, what frequency and voltage disturbances you have to be able to just withstand, and then how you should perform in different scenarios. Each one of those will have usually an automatic and a minimum access standard. The negotiated is by definition negotiated, so it's not defined, but that's usually somewhere between these two. In very rare occasion, you can see a negotiated access standard that's more onerous than an automatic access standard. Jumping into this a little bit more detail. So what are we doing and why? So usually when you're moving into dynamic EMT and RMS modeling, you're doing, if you're early stage, you're probably doing dynamic model acceptance testing. So there's AEMO have released a DMAT. Effectively, that's just a standard set of benchmark tests that anyone can do on any model. You don't have to know where you're connecting to the network. You don't have to know specifics. You could pick that up from, models from a manufacturer and start running that today. That was sort of developed with a view to having a standard set of tests and things that people could benchmark themselves on. The benchmarking bit is then, I'll call it out down here, but effectively you will have to provide PSCAD and PSSE models. They're two different software packages. PSCAD is EMT, PSSE is RMS. So pure time domain, propagating waves, all of that, versus everything's assumed to be 50 hertz. And you have to, as much as possible, demonstrate that they show similar performance. So they're in agreement. When you run different tests and different disturbances, they're aligned. From there, the first studies that you'll probably do that will be site-specific would be GPS compliance. So again, you'll have a proposed, this is what we think we can meet within the performance standard, and here's our models demonstrating that. And that's the first stage of that application process. You'll also then have grid forming. So one of the I guess, evolving areas and areas for inverter-based resources to demonstrate they either contribute to system strength or don't have a negative impact on system strength is to be grid forming. If you get the opportunity, I think Nathan Crooks, who's also on the Seagray NGN committee, has done some presentations that very worth looking at. And that's effectively just a mode of control and operation of inverters that avoids some of the system strength related stability issues that most inverters historically have had. The last bit of it, this EMT and RMS modeling, is that we do what's called a full impact assessment. So I called out earlier on a preliminary impact assessment, which is, I guess, tied to that grid forming bit that we were talking about there. Effectively, this is doing wide area studies, so it could be of the whole NEM, but usually it's sort of the network and generators in the area surrounding your connection. In our case, we'd probably model Queensland and maybe also down into New South Wales. And it's running, okay, if we put this generator in this model and we run a whole heap of different network arrangements and contingencies, what is the stability impact? And so that's looking at, is there interactions between generators in that area? Does it cause oscillations? Does it cause instabilities? I won't spend too much time on this. Effectively, why two software? Short answer is because that's the requirement, but effectively, to go into it in more detail, they exist to fulfill two purposes. PSSE is super fast. It's not like back of the envelope basic, but it's really fast. Again, if you're only interested in 50 hertz phenomenon, like your thermal constraints, general voltage response, all of that sort of stuff, runs stuff very quickly, and does dynamic control over the top of that. So it's actually trying to apply the control that the generator is doing and responding to different events. And you can run hundreds of studies in a matter of minutes. PSCAD is that, as I said, next level detail. It can take you minutes, tens of minutes to run 20 seconds of a study in PSCAD, depending on how big and complex your model is. So this is super detailed. Often does that next level in understanding stability, so large signal disturbances, stability. This one will do the, I need to know an answer right now, and it's therefore used quite often like operational settings. So I need to run a few different scenarios, and I can't wait 2 hours to get the results. Hopefully that gives you a bit of understanding of the different modeling that happens, why, what tools you're using, and what the purpose is. The last bit that I wanted to close out before discussion is opportunities for early career engineers. And first and foremost, I'd say like the most exciting bit for me is, while I probably haven't done it the credit that it deserves, it is actually a very interesting space to work in. And I would say, the energy transition is underway now. It's going to be a journey for at least, I would say, the next 15, 20 years. So it's something you could build your career around. And a big part of that energy transition is supporting connections of new generators. So I find, as now not so early career, young NGN engineer, but for me, that's one of the bits that really gets me passionate and interested in working in this space, because you are having an impact, you are supporting connections, you're working in a really interesting and developing space. On that front, it's a space that will require lots of people with know-how. So, I didn't want to put it down to specific skill sets, but there's a huge range of opportunities, ones that I've spoken a lot about today, ones that I've glossed over very briefly, but there is a lot of work to be done around generator connections, around generator operation, and probably drawing a longer bow around the energy transition. Looking more specifically at the stuff that I presented, I hopefully was able to articulate that I think there's a lot of opportunity to streamline some of these assessments. They are a significant time investment, potential cost, and delay risk. So, there is lots of consultancies that have spun up with skill sets just focused in this area around doing connection studies. I think there's opportunities to develop new skills and tools. So again, there's consultancies that have spun up just to provide tools to support doing generator connection studies, and to streamline that process. So it's not even that they're doing it; they're selling software and tool sets that help with that. And I think, as you know, the NGen being focused at early career young engineers, I think that's somewhere where the lack of history and the benefit of a new set of eyes is super beneficial, because you're not bound by thinking things have to work in a certain way. This one's sort of around the opportunity to I'd say generally do things better in the way that we offer connections. So whether that's financial side, in tariff offerings, in markets to sell the services, or just in general economics. So if you're sort of so inclined with more of the financial side of engineering, there's plenty of opportunities in that space to do things better. If you're more technically minded, as I said, the capacity and congestion management, moving from a system where we had several, so still many, but often quite large consolidated generators, to now having, a multiplier of 10 at least times more generators, but spread out across different areas, and how we manage that, how we manage the network investment, how we manage capacity in a cost-effective way that achieves about a good outcome both for networks, but also for proponents and for the end users is going to be a big area of work. And then lastly, had implementation of grid forming inverters. So I didn't do a lot of credit to this in the presentation, but for inverter-based resources, that's the sort of next Everest. It is sort of rolling out and demonstrating reliable grid forming operation, which just means they are not relying. So that the alternative to grid forming that you've no doubt already heard is grid following. So it relies on a heartbeat from the grid to continue to operate, and that's a substantial risk when you're going into weak areas, or when you're losing synchronous generators that are sort of synonymous with providing a strong heartbeat, because they're big machines, they've got a lot of rotating mass, they don't stop and start very quickly. So I think that's an area of really good technical R&D opportunity and opportunities for a lot of firsts to be explored. With that, I would say hopefully that's not put everyone to sleep. Throw it open for discussion for the time that we have left. Kunj, how did you and I?
Yes, so we have 3 questions. While you answer those, I will turn on the settings for everyone to unmute and turn on the camera so they can have a live discussion with you. So first question is,
fantastic.
First question is, what does steady state modeling of rejection mean? That was on your slide with detailed inquiry.
Yeah, so it's a concept that's usually applied to load, but it's effectively looking at what happens in the instant of the connection being rejected. So effectively tripping of a connection. And with really large loads, you get scenarios where, all of a sudden you could be supplying 50, 100, very big load. If that was to trip, either due to a fault in their own plant or something on our network, that causes a major disturbance. That's instantaneous drop of load, or in this case, it's the instantaneous drop of a generator and potentially the support that they're providing. What is the impact of that? And it's really looking to quantify that, usually in a voltage setting, to say, well, in that state, we'd get a bounce of 5 to 10% per unit voltage.
Awesome. So next question is, what are some of the common reasons that you will send back to the applicant at each of the R0, R1, R2 phases? And what suggestions do you have to prevent them holding back the connection process?
Yeah, that's a really good question. And that is definitely the $1 million question. So, look, I think this is part of the challenges and realistically the opportunities, is that working through this process is complex. It often involves a number of different people, often the people funding the connection. will have their own consultants because they're not the technical generator experts. They're the people that are funding the development. But just like you have when you build a house, you get a builder. When you have a generator connection and you're bankrolling that, you'll often have a consultant that does a lot of the technical assessment. I think more and more on the early stages, I think making from an NSP side and an industry, the more we can do to make information about our network available will hopefully drive investment in the right areas. And when I say right areas, I mean generally geographical areas, because this is probably even pre-R0. There's often a lot of investment and speculation in areas where it's just genuinely expensive to connect. There's no nice way to sell it. The network is maybe not suitable for large connections. So whatever we can do as an industry to make that more available and understandable for proponents. I think otherwise it is really, and I think there's been a lot of work done within the industry. So the DMAT was sort of a response to a lot of these modeling issues having to be identified through generator performance studies. So in that R0 to R1 stage, I think more we can do with that in offering sort of standard sets of testing, and AEMO is now offering. I would have to go back and check how far this has progressed, but effectively they were looking at offering the opportunity to submit your models and a connection location, and they would run effectively first pass studies. So you could do on demand assessment of your generator. So those sorts of things will definitely help. Unfortunately, there's the probably the other things is knowledge and experience help. So as we get, as consultants get more comfortable, as NSPs get more comfortable, as expectations are more generally understood, that just makes things work more smoothly. But unfortunately, I think with some of this, there's bits that are unavoidable, and that's often getting into the nitty-gritty of performance requirements and debating what's expected. So I think as much as we can, early information from both sides, but definitely in the early stage assessment and shared understanding, I think, in around expectations.
Thank you. Next question is, can you provide a quick overview of grid connection process for BESS less than 5 megawatt, non-scheduled, in terms of steady state and dynamic modeling requirements?
Yeah, so the short summary, mindfully, I'm running out of time. The short summary is a lot of the RMS modeling is the same, just at a different scale, at a different connection size. The EMT modeling, and this can be, it's probably getting into the point where it's less of an AEMO concern now. So anything greater than 5 megawatts has to be registered with AEMO unless they seek an exemption. Definitely anything larger than 30 meg is almost explicitly unlikely to get an exemption from registering with AEMO, but effectively for larger than 5 meg, there's a really well-structured and defined process. For less than 5, this is where I can probably say from Energy Queensland perspective only, but we've tried to apply a lot of that same consistency, acknowledging that usually the modelling and the due diligence and the back and forward around generator performance standards is a little less onerous.
Okay.
But similar is what I would say. RMS same, EMT similar.
All right. Next question is, I'm not sure if I understood this, but do projects that become committed and reserve capacity always get built?
Yeah, it's a good question. So it's not uncommon for them to hang around for a long time, either to firm up their financing or to be on-sold. I would say I'm not aware of any that have completely pulled out of having their committed generator, because that is worth a lot of money. And there's definitely been examples of where a generator has probably stagnated for several years, so 2 or 3 years before it's progressed in earnest through that R1 or beyond R1.
Awesome. Last question is, when you do an FIA for distribution connection, what's the extent of area you cover? For example, whole of Queensland or part of it?
So usually we'd do whole of Queensland for the model. If it's close to the New South Wales border, you'd also include New South Wales. Probably the flow on in that question is what are the contingency scenarios we look at? So you'd be looking at a sort of contingency range within a reasonable area. Obviously, if we've got a generator connection in sort of Cairns, you're not looking at contingencies on the transmission network out in southeast Queensland. So shorter answer there is that we would model at least all of Queensland, potentially more depending on the location. And in terms of the contingencies and operating scenarios we'd be assessing, that'd be maybe a bit more geographically focused. But usually that's decided as a part of going through that process as well.
Awesome. That was all mentioned in Q&A, but if anyone have a question, you can unmute yourself and have a discussion. We still have a few minutes.
I should say I'm also open to contrary or other perspectives, because I think that's the really good opportunity even for myself out of this, is to hear if others have had different experience or thoughts.
I have one thought if you want to hear that. Yeah, it's about the knowledge retention or successive planning.
Yep.
Because what I have felt is I have got the same question from all the connection applications from different engineers, because the employment stability is reducing with time.
Yep.
So it's a bit hard for consultants and developers to repeat the same sort of fixing issues, and it just delays project a lot.
Yep.
And it's just circling around the same issues. And so I was just commenting, and if you have any thoughts on that, or have you got any policies to retain knowledge or successive planning?
Look, that's genuinely so. I think, again, speaking specifically to distribution business, this is an area that's had to grow over the last 10 years. So distribution businesses didn't do 100 megawatt generator connections, more than 10 or 15 years ago. So it's been a knowledge build and to some extent a knowledge borrow from other businesses, like transmission businesses that more regularly did this. I think as an industry, though, as you point out, Kunj, the need for that knowledge and the value that knowledge has means that there is a lot of headhunting and poaching and, even just people progressing through their careers because that knowledge is super valuable. For me, I see that as an opportunity. To your question, though, how do we stop that? I think as organizations, and this is across the industry, the challenge is going to be acknowledging and rewarding that knowledge and that understanding in a way that's going to keep people around. Otherwise, from there, if you can't stop churn of people, it's really down to all of those other things that we should be doing anyhow, which is documenting as much as possible, capturing knowledge in a way that's consistent and transferable. But again, often those things. Sometimes those things can become the enemy of a quick delivery because, if you're just churning stuff out, it's often easier to do it in a way that you understand and then know and reach a point where you're happy to do that in a way that's then documented so anyone can understand it is an actual investment. So I think it's definitely a challenge. 100% we've seen the same thing. So much so that in my team in the last month, I think there's been 4 or 5 engineers move on to different roles, and that's a real impact. That's a huge amount of knowledge that's moved. I try and look at it from the positive side, that I think this, again, to the opportunities for early career engineers, super valuable, and the skills you build are highly sought after. So I think that's an opportunity, hopefully for everyone on this call, if you're working in that space or if you aren't already. Challenges for organizations and the industry to, as you say, deliver consistency. Sorry, mate.
That's all right. We are a bit over the time, but your last question, if you want to close out answering that is there any recommendation for best way to learn PSCAD and PSSE modeling for connections?
Yeah. What I would say is PSCAD, I have to check PSSE, but PSCAD offer free licenses. And those licenses, I haven't checked recently, but I think they're normally sort of robust enough to actually do a lot of your own modeling. This is not a plug, I should say. So plenty of other softwares do EMT modeling. Power Factory does it, all that sort of stuff. But PSCAD is effectively the industry standard for Australia for EMT modeling. Manitoba Hydro, who build or who own and write PSCAD, they have a lot of tutorials on their page, so that just gets you into using the tools. Moving beyond that, often the challenge is getting access to original equipment manufacturer, so OEM models, which there's no real OEMs that are going to throw their models out publicly because there's a lot of IP that's built into that and a lot of secret source and know-how that they don't want others to steal. But what I would suggest is there is, again, Manitoba Hydro have grid forming generator models that are just on their website. Often researchers publish models. So I'd pick up a couple of those. Have a look at the Dynamic Model Acceptance Test Guideline. It is a lengthy document with hundreds of tests. But if you look at some of the ones that are doing voltage disturbances and all of that, or withstands, they're good places to start and just have a crack at running some models and see if, can I run a disturbance? Can I get this generator to perform as expected? And that's a really good self-led learning way into doing it. Obviously, there's plenty of courses and all that jazz.
Awesome. Thank you. I hope that everyone's got their answers and they expect. If not, then you can contact us or you can email Matthew. The slides will be available on KMS page if you're already a member of Seagray.
Cool.
And we'll.
I was going to say the last bit I'll just throw up for the recording in case anyone's just watching that. These were a couple of the references that if you want to learn a little bit more about the process and the modeling and all of that, check out those websites.
Awesome. And we'll try to post a YouTube video based on this recording if you want to check this later. And thank you everyone for joining, and thanks Matthew greatly with all the time and enlightenment.
No worries. Thanks for the questions and appreciate the discussion.
Awesome. Thanks guys. Have a good weekend.
See you.
Bye.